Okay. Hello. This is Mr. Kramer again. I'm just going to be going over a brief introduction into molarity, though for today I won't be talking too much about molarity. Mostly this will be a review of what moles are and how to find them using the molar masses on the periodic table. So let's get started. So first thing, why do we care about moles again? We learned about them a long time ago, and we're going to put them to use finally here. So we've been learning a decent bit about solutions. Particularly, we learned about solubility. We talked a decent bit about what the dissolving process looks like. We learned that the polarity of water is really important for helping to pull those molecules apart into solution. And now we're going to get to sort of the science side of things. That is the lab side of things. When we have actual things dissolved in solution and we want to describe them using, quantitatively, how much is dissolved, where it's dissolved, what's dissolved, that sort of thing. Okay, so molarity is this word that we get thrown around a lot and where you're going to be finding and using a lot. And I just wanted to go over what it was. So first of all, molarity is just how we measure concentration. You know what concentration is. You've had... If you've ever mixed up a juice from concentrate, you know that you have to add a bunch of water to it to get the right concentration so that it tastes good. Basically, concentration is the strength of a solution. In science terms, we define it as how much solute is dissolved into a solution, and the solution has a solvent as well. For us, almost every time that's going to be water is the solvent, and so the solution is that solute dissolved in the solution. So here's a couple of examples of solutions. On the left, you see there's less stuff dissolved, and on the right, there's more stuff dissolved. So we call the one where more things are dissolved, we say it's a concentrated solution. So the more concentrated a solution, the more solute is dissolved, and therefore the higher the molarity. Remember, molarity, which is what we're learning today, is just a measure of concentration. Okay, and so if we have a dilute solution, or if you took a concentrated solution and diluted it by adding water to it, you would end up with a lower concentration because it has less solute dissolved, and it's called a dilute solution, and that's measured with a smaller molarity. Now, you might be wondering, okay, I know that molarity is... Oh, my thing's in the way. Let me move my camera right here for a sec. The question of the day is, how do we actually measure molarity? We know that it's a measure of how concentrated a solution is, and we know from our own life experience that you can either dissolve a lot of something into water or just a little bit of something. Maybe you're trying to dissolve some sugar in your tea or coffee, and you dissolve a lot of it versus a little bit. Well, if it has a lot of sugar dissolved, that's a high molarity. If it has just a little bit of sugar dissolved, it's a low molarity or a dilute solution. So, So the way we measure molarity, well, guess what? Moles are back. Measuring concentration the way that we want to with molarity requires basically counting up all the solute particles that have been dissolved. Now, I don't just mean how many little grains of sugar you dissolved in your tea. I mean how many molecules of sucrose have actually been dissolved into the solution. There's no way we're actually going to be able to count that because there's way too many of them. So to make that counting easier, we're going to use moles to count how many particles of solute that we're dissolving. And the way we do that is by measuring the mass of the solute that we add. Say, I'm going to add a few grams of sugar to my tea. And then I'm going to use the molar mass of that chemical, and I find that molar mass from the periodic table. So we're going to need to review how to find moles using the molar mass and some given measurement. So, next slide. This is the periodic table as we know and love it. Frequently, this number in the bottom here on each of these boxes tells you the molar mass of each of these chemicals. So the molar mass, for example, of carbon is 12.011, and the units for that are grams per mole. I can move my head back probably where it belongs. Here we go. All right, the units for that are grams per mole. So that means that in 1 mole of carbon, there's 12.011 grams of carbon. And so we're going to use that fact to help us convert between grams to moles or from moles to grams. Remember, the reason we wanted moles in the first place is so that we can find a molarity. And we're going to get to that in another video. But for today, we're just going to focus on finding moles. So first thing, in order to find the molar mass of a molecule, I need to add up the molar masses of the individual atoms. So the periodic table is great. It gives me the molar mass of each individual atom, but most molecules are made up of more than one type of atom. So we're going to have to add those up individually to keep track of the molar mass of the whole molecule. So I'm going to do an example here with sodium chloride. So if I wanted to find the molar mass of sodium chloride has a formula NaCl. It's got a sodium ion and a chloride ion. We saw this in our previous video with molarity. And so in order to do that, I need to recognize that this has one sodium atom for every one chlorine atom. So that's one sodium for one chlorine. So I'm going to need the molar masses of both sodium and chlorine. I'm going to have to look in the periodic table for that. So let me go back to here. Sodium is over here on the left side. It's a metal, and it's got 22.99. I'm going to round that up to 23. And then chlorine over here has a molar mass of 35.453. I'm going to round that up to 35.5. When you're doing these problems on your own, there'll be some lenience with rounding, or we'll just give you the molar masses. If we give you the molar mass, then use the one we give you. If you're using your own periodic table, then just you can do a little bit of rounding is fine. Okay, so here's 23 grams per mole for sodium, and then I have 35.45 grams per mole for chlorine. And then there's one sodium and one chlorine, so I don't have to do any multiplying. I just have to add them together. So together, 23 plus 35.5, well, that totals to 58.5 grams per mole, and that is the molar mass of sodium chloride. So every 1 mole of sodium chloride weighs 58.5 grams. So that's one example of finding molar mass. I'm going to do another one where it's just a bit trickier. So let's find the molar mass of iron oxide, which is also rust. So if you imagine you had a pipe, well, this is a copper pipe, but imagine you put a steel pipe into your home, and then over time, just no matter what, it's going to get rusted. And so we wanted to find the molar mass of that rust chemical that was stuck to the outside of our pipe. So what you'll notice is these little subscripts remind us that iron oxide has 2 iron atoms and then 3 oxygen atoms. So when we're finding the molar mass, we're going to have to add up those numbers. So first we find the molar masses of both chemicals on the periodic table. And so we can go back to our periodic table and do that. Iron is here in the middle, has a molar mass of 55.845, so you could round that to 55.8. And then oxygen's in the top right here. It's got a molar mass of 15.999. We'll just round that to 16 because it's pretty close. Again, if you're doing it on your own, you don't have to round. I'm just doing it to make the numbers easier to look at. So iron has a 55.8 grams per mole, and oxygen has 16 grams per mole. So what I'm going to do is I'm going to take 55.8 and I'm going to multiply by 2. And the reason I multiply by 2 is because there's 2 iron atoms in rust. I'm going to need to move my picture again. Bam, go over here. And then for oxygen, I'm going to do the same thing. So 1 oxygen weighs 16, but I don't have just 1 oxygen atom. I have 3 of them. And so because I have 3 of them, I'm going to multiply this by 3. So 55.8 times 2, that's 111.6 grams per mole. 16 times 3, well, that's 48 grams per mole. And I'm going to add these two together. So this number plus this number added together, that's the total molar mass of iron oxide. So it's 159.6 grams per mole. Notice that this number is way bigger than what we found for salt, or sodium chloride. So 159, that's almost 160. Compare that to sodium chloride, which was only 58, so less than half. So depending on what chemical it is that we're talking about, the molar masses can be very different. And so that's why it's important that we find it later. It's going to affect how we calculate the concentration. So now that we know how to find the molar mass, we want to be able to convert from grams into moles. So say I added 5 grams of sugar or something into some water. I want to be able to find out how many moles that is. Or on the other hand, let's say that I already knew how many moles of salt I had in some water, and I wanted to know how many grams of salt that really was. Grams is something we can measure with like a scale, but moles is a little bit trickier. So let's start by finding the grams if you already have the moles. I think this is the little bit easier way. So if you're given moles, you already know how many moles you have, and you need to find grams, all you have to do is just multiply by the molar mass, which is pretty simple. So this is the formula here, grams equals moles times molar mass. And then the example that we're going to use is, say I wanted to find the mass of 3.5 moles of water. Let's say someone said you had 3.5 moles of water, and you're like, I don't really know how much that is. I want to be able to measure that. So you're going to need to use the molar mass to convert. So I've found the molar mass for water. It's 18 grams per mole. You can actually just Google this almost every single time. So if you're doing problems later and you don't want to go through the process of finding the molar mass, you can go ahead and Google this. Or you can do the process we just found. Water is H2O, so that would be 2 hydrogen atoms and 1 oxygen atom, and it'd be pretty close to 18 grams per mole. Okay, so I'm going to use this equation. Grams equals moles times molar mass. So grams equals moles times molar mass. Grams equals, I'm going to substitute. I had 3.5 moles, and then my molar mass was 18 grams per mole. So I'm going to multiply 3.5 times 18. Those moles are going to cancel out, and I'm going to get 63 grams. So basically what this is saying is that 3.5 moles of water is the same thing as 63 grams. So that's just one example of going from grams to moles. I'll probably show some more next week, but I wanted to jump ahead and do an example of going from moles into grams. So finding moles from grams is sort of the other way around. And like math, you know, when you do things the other way around, the process is a little bit different. So if I have grams and I need to find the moles, I just have to divide by the molar mass. So last time we multiplied by the molar mass, now we're going to divide by the molar mass. So the formula is similar. If I want to find moles, which I have over here on my left, then I just take the grams that's given to me and I divide by whatever the molar mass is. So as an example, let's say I wanted to find out how many moles are in 50 grams of nitrogen gas, or N2. So if I wanted to find the molar mass of nitrogen gas, I could go back to my periodic table. Nitrogen here has a 14.007 grams per mole. I can just round that up to 14, and then I have 2 of them. So nitrogen gas has a 2 there. It's called diatomic. And so 14 times 2, well, that's 28 grams per mole for nitrogen. So I'm going to use this formula. Moles equals grams divided by the molar mass. Well, I'm given the grams, that's 50. So I'm going to take 50 grams. I'm going to use that 28 number that I found by using the periodic table. So 50 divided by 28, and that's going to give me the number of moles. The moles is 1.79 moles. Moles of N2, I could actually edit this to say. And so that's really going to be useful. This moles number is going to help us find later the concentration. Let's say I was trying to dissolve this gas into some water. Even though I knew I had 50 grams of N2, what I really need is how many moles that is to appropriately find the molarity, which is really the goal of this unit. So look forward to some videos talking about finding molarity from moles, or working backwards, taking some solution and figuring out how many grams of sugar or salt or whatever you had dissolved into that solution. If you have any questions, feel free to email me or Mr. Ellingson. Yeah, and have a good one. Thanks.